A sequence is a set of numbers ordered by a specific pattern. An element of a sequence is referenced by its index. For example, consider the sequence a sub n is equal to n, starting at n equals 0. The terms in this sequence are 0, 1, 2, 3, 4, 5, and so on till n. The first term, a naught, or a sub 0, is 0. Convergence is when something approaches a defined value. Divergence is when something approaches infinity or becomes undefined. A sequence is convergent when the limit as n approaches infinity of the sequence converges to any number. A sequence is divergent when the limit as n approaches infinity of the sequence diverges. The series, represented by the capital letter sigma, is what sums the terms in a sequence. We are used to considering partial sums, which only add up a set amount of terms in a sequence. However, with calculus, we can consider infinite series that sum all terms in a sequence from n equals 0 to infinity. Series may converge or diverge, and there are many tests we can use to determine this. The nth term test, also called the divergence test, takes the limit as n approaches infinity of the sequence within a series. If your sequence approaches a non-zero number, you will keep adding terms to your summation forever, and thus the series will diverge. Thus, if the limit evaluates to anything other than 0, then the series diverges. However, if it does evaluate to 0, the test is inconclusive, because the limit may fail to consider rapid oscillations or fluctuations of the terms in the sequence. A geometric sequence is a sequence with a constant ratio between successive terms. A geometric series sums the terms in a geometric sequence. The general form for an infinite geometric series is the sum from n equals the starting value, or starting index, to infinity of the sequence a times r to the n, where a is the first term in the sequence. For example, the geometric series that sums the sequence 1/2 to the n is geometric, because each consecutive term is multiplied by 1/2. If the magnitude of the ratio is less than 1, the terms added become continually smaller, so the series must converge. However, if the magnitude of the ratio is greater than 1, the terms added become increasingly bigger, so the series will diverge. The geometric series test, or GST, states that if the magnitude of the ratio, the absolute value of r, is less than 1, then the series converges to the first term, a, divided by the quantity 1 minus r. We can also consider the integral test, which works for a continuous series with positive, monotonically decreasing terms. Rewrite the series sequence as a function of n, or really any variable, it's just a dummy variable in this case, and then integrate the function from the series starting index to infinity. When considering the sequence as a function f of n, the series represents the Riemann sum under the curve, while the integral is the actual area under the curve. If the integral diverges, then the Riemann sum also diverges, because it indicates that the rectangles are growing in height as the function approaches infinity, and thus the series diverges. Applying the integral test to a series whose sequence is in the form of 1 over n to the p, these series are called p-series. We can implement the p-series test. For any p less than 0, the fraction flips, and applying the integral test will easily imply divergence. For any p between 0 and 1, the series will also diverge. For p equals 1, the series will still diverge because integrating 1 over n to the 1, or just 1 over n, results in the natural log of n, evaluated at infinity, which will result in divergence. The series of 1 over n is called the harmonic series, and it relates to the harmonic mean of numbers. For any p greater than 1, the series will converge. For a series whose sequence, which we will call a sub n, involves some part of it being raised to the nth power, we can use the nth root test, which states that if the limit as n approaches infinity of the nth root of the absolute value of a sub n converges to anything less than 1, then the series of a sub n will converge. If the limit converges to 1, then the test is inconclusive, and if it turns out to be anything greater than 1 or diverges, then the series will also diverge. It is important to note that for a function f of x, which is equal to x to the quantity a divided by x, where a is some non-negative number, the limit as x approaches infinity of f of x converges to 1. This limit can be evaluated using logarithms and L'Hopital's rule. series whose sequence is in the form of a sub n minus a sub n plus 1, or the current nth term of a sequence minus its next term, we can use the telescoping series test. If the limit of a sub n as n approaches infinity converges to some number L, then the sum of the series is a sub 1, or the first term, minus L. The trick to this is simply canceling out repeating terms in the summation of the sequences. We can also directly compare series. The direct comparison test sets up an inequality between two series. Consider the series S and what we will compare it to, the series T, such that 0 is less than S, which is less than T. If the large series T converges, then the smaller series S also converges. If the smaller series S diverges, then the larger series T will also diverge. For a series with messy sequences with polynomials of many terms in the numerator or denominator of the sequence, we can use the limit comparison test. Consider a series with a sequence a sub n which we will compare to another series of another sequence, b sub n. Taking the limit as n approaches infinity of a sub n over b sub n, if the limit converges to a finite number L such that 0 is less than L, which is less than infinity, then the series of a sub n will meet the same condition as the series of b sub n. For example, if the limit converges to a non-zero value and the series of b sub n diverges, then the series of a sub n will also diverge. If the series of b sub n converges, then the series of a sub n will also converge. Essentially, the limit comparison test compares the ratio of terms between two different sequences, and if the two terms are of roughly the same size, then their series will behave similarly in terms of convergence and divergence. Some series may have sequences that have both negative terms and positive terms. For sequences whose terms oscillate between positive and negative values, we can use the alternating series test, abbreviated AST. By the way, an oscillation in a sequence can be due to a part of the sequence like -1 to the n or the cosine of n times pi, which make the terms go from negative to positive, and so on. Consider the series with the sequence -1 to the n times a sub n. When using the AST, we only consider the absolute value of the sequence, which is just a sub n, and it must meet three criteria. The first is that a sub n must be monotonically decreasing, a property of convergent series that alludes to the ratio test. This decrementation can be written as 0 is less than a sub n plus 1, which is less than a sub n. The second criterion is that the limit as n approaches infinity of a sub n must be 0, because you can't expect convergence by adding non-zero terms at infinity, as discussed in the nth term test. Finally, the terms in a sub n must be positive. If these three criteria are met, the series of -1 to the n times a sub n converges. It is important to note that AST does not imply divergence. The alternating series error bound can be used to bound how far a partial sum is from the value of the actual infinite series. For an alternating series S with the sequence -1 to the n times a sub n with a partial sum S sub n, the remainder R sub n is defined as S minus S sub n. If S converges by the AST, then the magnitude of the error of S sub n is approximated as the magnitude of R, or absolute value of R, is less than or equal to the next term, a sub n plus 1. The more terms that are added in the partial sum, the less error is generated. A series may be divergent, conditionally convergent, or absolutely convergent. For an alternating series S, the series will conditionally converge if it converges by the AST, assuming a series S has a sequence B sub n, which is equal to -1 to the n times A sub n. Taking the absolute value of B sub n implies that the absolute value of B sub n is A sub n. If the series T with the sequence of the absolute value of B sub n, or rather the series of A sub n, converges, then the series S is said to absolutely converge. Thus, the condition in conditional convergence is whether the series alternates or not. For example, the series of the sequence -1 to the n over n conditionally converges. Absolute convergence implies conditional convergence, but not the other way around. The last test for convergence we will consider is the ratio test. For a series S with a sequence of A sub n, we will take the limit as n approaches infinity of the absolute value of A sub n plus 1 divided by A sub n, or in other words, the magnitude of the ratio of the next term over the nth term as n approaches infinity. If the limit converges to a value less than 1, then the series converges. If the limit diverges or is greater than 1, the series diverges. If the limit converges to 1, the ratio test is inconclusive. Essentially, the ratio test examines the extent to which the terms are decreasing. If the ratio as A sub n approaches infinity is less than 1, then the terms are decreasing, and adding continually decreasing terms implies convergence of a series. If the ratio is greater than 1, then we are adding continually increasing terms in a series, implying divergence. If the ratio is 1, we had to use other tests to determine convergence or divergence. Functions can be represented or approximated by series. For example, a function f of x may be represented in whole or by part through what is called a power series. The general form for some power series which equals f of x is a sub n times the quantity x minus a, where a is the center of the power series with respect to the function. A sub n is part of the general sequence, and x is the variable that produces different values of the series, as it does for the function f of x. Think of the power series as drawing a part of the curve of a function. It is most accurate in drawing at the curve at x equals a, where the series is centered, but when moving x far from a, the power series will diverge, or in other words, will not match with the curve of the function. If a power series converges, then it converges at a single point x or over a certain interval. The interval in this case is all the x values such that the series converges and matches the curve of f of x. To find the interval of convergence, we must find the radius of convergence first, which can be done through the ratio test. When taking the limit of the power series sequence, treat the x minus a part of the sequence as a constant, since we are taking the limit with respect to n as it approaches infinity. When factoring out the x minus a, we must ensure that it is the magnitude of x minus a, or the absolute value of x minus a we are factoring out, because the ratio test takes a limit of the term's absolute value as it approaches infinity. Assuming that the limit evaluates to L, then the power series converges when x minus a times L is less than 1. From here, solve for the absolute value of x minus a, which gives you your radius of convergence, r. It is important to note that if the limit diverges to infinity, then the power series converges only at the point where x equals a. If the limit converges to 0, then the power series converges for all x, because the absolute value of x minus a times 0 is less than 1 for all values of x. Once we have our radius of convergence r, we know we can find our endpoints by adding and subtracting it from our center at x equals a, or in other words, solving for when the absolute value of x minus a is equal to r. Endpoint behavior can be iffy with power series, so we must test our endpoints by substituting them into the variable x in the original power series. If the endpoint causes the series to diverge, it is considered an open endpoint on the interval of convergence, and if the endpoint causes the series to converge, it is considered a closed point on the interval of convergence. Using a known series, a power series for a function can be derived using operations like differentiation, integration, or various algebraic techniques. For a function f of x represented by the power series s, its derivative, f prime of x, can also be represented by power series t, just by differentiating the original power series s. If we were to differentiate each term of the power series S, or rather the added terms of the sequence, it would be the same as differentiating the series' original sequence in terms of n with respect to x. In summary, just check your ddx into the summation and differentiate the sequence itself. The same applies for integration. However, when integrating a power series, we must account for the constant of integration, c. The notation is to just add the plus c before the series, so c plus whatever your series is. The radius of convergence for a differentiated or integrated power series is the same as its parent or child function's power series. However, endpoints still have to be tested, as they can be different. A special case of a power series is the Taylor series, whose radius of convergence is infinity. Taylor series are derived by taking higher order derivatives and solving for them where the Taylor series is centered at. Consider the Taylor series whose general sequence is c sub n times x minus a to the n, where a is the x value that the Taylor series centers on a function f of x. Writing out this Taylor series, we get c naught plus c1 x minus a plus c2 times x minus a squared plus c3 times x minus a cubed, and so on up until c sub n times x minus a to the n, all of which is equal to some f of x. Note that this expanded form of the Taylor series is called a Taylor polynomial, and it's really just an nth partial sum of the series denoted t sub n. If we wanted to solve for c naught, we would plug in f of a, and the rest of the terms that have x minus a would cancel, so we would just end up with c naught. If we wanted to solve for c1, we would differentiate this entire Taylor polynomial and end up with c1 times 2c2 x minus a times so on up until n times c sub n times x minus a to the n minus 1, all of which is equal to f prime of x. So if we wanted to solve for c1, we would just plug in x equals a, and c1 would be equal to f prime of a. Continuing to find higher order derivatives for our Taylor polynomial, we notice that the powers of x minus a will cascade down in a factorial-like pattern. Thus, when solving for c sub n, we find that it is equal to the nth derivative evaluated at a divided by n factorial. So the general form of the power series, or rather the Taylor series, is a sum from n equals 0 to infinity of the nth derivative evaluated at a divided by n factorial times x minus a to the nth power. Taylor polynomials up to a certain n can be used to approximate the values of transcendental functions whose values are hard to compute by hand. However, these polynomials only work for values centered near x equals a. The more terms in the Taylor polynomial, the more accurate values further from x equals a can be approximated. To approximate the error of a Taylor polynomial, we must define our remainder, or error, function. The function f of x is equal to the polynomial approximation t sub n of x plus the remainder r sub n of x. Solving for r, we find that r sub n of x is equal to f of x minus t sub n of x. This is the exact error, but when we cannot compute the actual value of f of x, we must use the Lagrange error method to bound our error. We approximate the error by stating that it is less than or equal to the next term, which is quite similar to the alternating series error bound method. In fact, in some situations, the alternating series error bound can be used to approximate the error of a Taylor polynomial. Since the remainder Rn of x is less than or equal to our next term, using the general form of the Taylor series, our remainder Rn of x is less than or equal to the next derivative evaluated at a point z times x minus a to the n plus 1, all divided by n plus 1 factorial. Note that z is the x value that gives the max value of the next derivative on the interval, such that z is between a and x, or equal to those two values. We find the maximum of our next derivative because we want to find the maximum possible error generated by the Taylor polynomial. A special case of Taylor series is the Maclurin series, whose a value is 0, or in other words, it is a Taylor series centered at x equals 0. For the function sine of x, its Maclurin series is the sum from n equals 0 to infinity of x to the 2n plus 1 times negative 1 to the n, all divided by 2n plus 1 factorial. For cosine of x, it's the sum from n equals 0 to infinity of x to the 2n times negative 1 to the n, all divided by 2n factorial. For for the function 1 over the quantity 1 minus x is the sum from n equals 0 to infinity of x to the n. And finally, for e to the x, it's the sum from n equals 0 to infinity of x to the n over n factorial. Plugging in ix into the Maclurin series for e to the x, where I is the imaginary unit, and rearranging the terms generated by the series, we find that e to the ix is equal to the cosine of x plus I times sine of x. Plugging in pi, we find that e to the I pi is equal to -1, and thus emerges Euler's identity, which is e to the I pi plus 1 is equal to 0. Calculus is elegant and easy.